Hello everyone, let's go again for another class of our program, Foundation Engineering. And we are still on chapter number 2, the in-situ soil testing chapter, okay? So from this video, we will start talking about different type of investigation, okay? This one will cover the geophysical testing method. There are several methods, geophysical testing method. We are going to try to cover all of them in this video, okay? So it will be only one video in this point number 3, okay? So the geophysical testing methods, how many are they? The first one will be ground penetrating radar. This ground penetrating radars are shown in this figure. This is just example, okay? You can find many types, but this is typical one. So this I will call it GPR, okay? GPR is a geophysical tool that provides a graphical cross-section of subsurface condition, okay? It uses a repeated short duration electromagnetic waves generated by an antenna in the contact with the ground to create this kind of view. See? So right now, there are even some drones that can do this, okay? And you can see here the path of this machine, okay? Scanning all the field. There is, I think, spacing about 10 feet, okay? The spacing between this and this. So the reflection of these waves occur at interface between the soil material and different with differentiating electrical property. It means different type of soil will have different type of electrical property. Okay, especially especially variation in the electric permittivity, which is linked to electrical conductivity. Okay, so here is how it works. Like if we have one soil layer here, another one here, this is surface. Okay, so transmitters, the transmitter is here, will transmit, okay, these waves, and they are reflected like this, okay. If the wave encounter soil change, like layer change or any obstacle, it will just reflect the wave like this. It will change the direction, going to receiver, something like this, okay. And then processor and output, you will see output. So there are different types, of course, different types of this machine with different capacity and different penetration depths, as you can see. And also, this dot, it just means the object, okay? The object that the machine can detect, okay? There are different types. So if you want to go deep, you better take the one that can go deep in the ground and can detect large size objects, okay? So this GPR is commonly used to locate underground utility as well, like pipelines, okay, storage tanks. You will see something like this. So if here we have, for example, a pipeline, So if you use the machine, as you can see, this is another type of this machine, GPR machine. It can show you that at this location, you will see something like this. This will, on your screen, directly, you can see this something like this, telling you that at this location, there is something, okay? You should be careful. So before digging anywhere, you can check this, okay? So this information helps to decide where to apply more invasive techniques, such as boring, or like if you want to do any like CPT or SPT, you can after scanning the ground, the field, you can know that this place we have buried like a pipeline or tanks or some object in the ground. Okay, so this GPR unit includes integrated electronic component that transmit high frequency. The frequency can range from 100 to 1000 and 1500, something like that, wave into the ground. Okay, so as I explained before, so you can choose the one that is convenient for you. When there is a little or no electrical contrast, it becomes difficult or almost impossible to identify the object using the GPR. Okay, the system comprises an antenna which act as both transmitter and receiver, and a profiling recorder that process the data and provide geographical display. Something like this, you can see here is an example of a GPR image. You can see very clearly different type of soil layers. Okay, this one is the first soil layer. You can see here the curve also. So background noise level before transmitter, uh, it's around 0.9 something. Okay, so you can see the difference between the signal, the amplitude of the signal. Okay, the peak is here. So each soil layer, each type of soil has different way of different having different property will give you something else. Different will modify the curve so that you know that here I have this, here I have this. Okay, so despite this, GPR is very useful for detecting soil change. Okay, it can tell you this soil here is different than this soil here. You can know the different soil layer, the thickness also of the soil layer. Okay, but problem is it cannot help you to identify the nature of the soil or the condition of the soil. Okay, it cannot tell you that this is sand or this is clay or this is this. The only thing it will help you to do are like these things. Change the strata thickness. You can see clearly here the thickness of this soil layer. Okay, subsurface anomaly, maybe if something is in the ground, you can see here there is something, we don't know what it is. So sometimes also it can help for other fields also, not only geotechnical engineering. But anyway, for the for you to be able to identify the soil property, the type of soil, you need another type of testing method, not this one. Okay, so it is best than to use, okay, these techniques, this GPR, to combine it with test the cross section profile. Okay, other geotechnical and physical tests. You combine this GPR test with, for example, CPT or SPT test or any other test that can help you, because it will not give you the soil property. Okay, So we'll see another test, which is here resistivity test is. This is not only one test, but there are different types. First one we will see, okay, but the resistivity test is like electrical resistivity imaging maps, okay, that maps the difference in electrical property of geological material. So soil, different type of soil will have different type of electrical property, okay. So the water content, pore water chemistry, and buried debris lithology, okay. This, because of this, the soil will have a soil will have different property than another soil, okay, because of this type of uh, factors: lithology, water content, pore water chemistry, and maybe debris, buried debris, okay. So we use this device to do the test, resistivity test of soil, okay. I will explain soon how this works, but it involves transmitting an electric current, okay, like electricity with a certain amount of intensity, the current intensity, and you measure the voltage between the electrodes. These are the electrodes. See, electrode, okay. So the thing is, the electrical resistivity we will notice here of any soil, any material having length L and area like cross section A can be defined as this formula. This is not only about soil, okay? Any material, for any material, if you have the length of the material, the cross section of the material, you can measure the resistivity of that material, okay? This formula is a general formula, okay? So uh, this R is just electrical resistance, okay? When you, the electrical resistance. L is the length, A is the cross section of the material. So you can measure the resistivity of any material. In this, for soil, I will show you how we do that, how we measure the resistivity, I mean the electrical resistivity of soil, okay? So I will put back this figure here, and I will simplify this here, this drawing, with this drawing, okay? We have four electrodes, 1, 2, 3, 4, okay? So I will model them like this. The two out, like the outside electrode, this one and this one, okay? The green one and red one here, you see? So it's very important to keep same distance. You can see here D, 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 the four electrode, okay? So the two outside electrodes send electrical current, okay? The current will be sent. You see here, the current will be sent here. Okay? And the current is typically between 50 and 100 milliamperes, okay? DC current, not AC current, not alternating current. So you send this current into the ground using this the outside electrode, okay? And the voltage drops, V, voltage drop V is measured between the two inside electrodes, means this one and this one. You can see here V. We want V here, the voltage here, V. Okay, this device will measure this for you. So if your soil is uniform soil, uniform homogeneous soil profile, then it will be easy for you to find the resistivity by using this formula. Okay, very easy. The resistivity will be 2, this is pi, and this is d, the same distance here, you can see d. Okay, and I is just the current. Remember this current you've sent here, and V is the voltage you will measure here. That's very simple. So if the soil is uniform ground, soil is uniform, you can measure the resistivity using this. Okay, but we all know that on the field you will not have uniform ground, you will have different soil layer. Okay, so in that case, if you have layered soil profile, this equation will not give you the actual resistivity. It will be just be like apparent resistivity. Okay, so how do you find then the actual resistivity of the soil and the layer thickness? For example, we have here 2 soil layers, the first layer 1 and layer 2. Okay, you have the G1, the thickness of the first layer is here, and the bottom layer is here. So how do we find the thickness G1 and the resistivity of the 2 soil layers? Okay, in that case, what you have to do is change the value of the spacing. Okay, different the electrode spacing, you have to change the spacing and plot the sum of apparent resistivity against D. Okay, for change D, you measure this, you measure V and calculate the resistivity corresponding. You can get 1 dot here. Okay, D measured resistivity. Don't forget that you are summing, you are additioning everything. Okay, because you can see here the first one, since it is the first one, it has to be something. Okay. Second, you change again the D, change it and get another. Of course, when I say change, you can just guess that it will be increased the D, like double it. Okay, as you can notice here, the value of D is changing, is increasing. Okay, and you will get this kind of curve. Okay, so this curve will give you the slope of this curve will give you the resistivity of the soil. The slope of this one, this segment will give you the resistivity of the first layer, the top soil layer. Okay, and the slope of this second segment will give you the resistivity of this second layer. Okay, and the thickness of the top layer is just this distance. You see, Z1 is this distance. So this is when you have 2 soil layers, several soil layers. Okay, so then by varying the electrode spacing, you can create 1D geoelectrical cross section. Okay, but there are also some advanced technology that can allow you to get rapid collection of data along the transect and get 2D geoelectric cross section. Okay, here is an example of this using this method, the cross section, 2D cross section we can get. You can see different type of soil here. Okay, this is silty, sandy clay, peat and clay, sand component soil. You can see even like water level or something like that. So And you can see here, it measure in ohm meters. Ohm is like you can see here, because R is resistance, electrical resistance, which is measured in ohm, right? Ohm. And this is area divided by length. Square meter divided by meter, it will be meter, right? So that's why you have here ohm meter. Okay, so you can see, the thing is, this value will tell us, can even tell us the type of soil we are dealing with. Okay, the ranging of this. Okay, as you can see here, this table is giving us, for example, for sand, it will range like between 500 to 1,000 something 500. Okay, the resistivity. So let's check this here. We have here sand. Okay, and if we check here, maybe the green one is sand. See, between here is 300. Maybe just above that is like this space, this interval. Okay, clay, sand, gravel. Okay, wavered rock, sand rock. These are just typical values of resistivity of soil material. Okay, let's talk about uh, another method again, which is seismic refraction. What is seismic refraction? Seismic, maybe you know already. We will use the wave, seismic wave, P wave or S wave. Okay. The seismic refraction technique measures seismic velocity. Okay. Seismic velocity of model. To model the depth of surface interfaces, okay, inferring soil condition and geologic structure from changes in seismic velocity. Okay, this here are like equipment used for this kind of test, seismic refraction. Okay, there are some like this hammer. You will see why we need this hammer soon. Okay, and here is just small scale test being conducted. So you can see the hammer, how he is using hammer to hit, to create wave. Actually, this hammer is used to create seismic wave. And here is how it works. So you hit here, okay, using the hammer, hit here, and the wave will travel in the ground. And you can see, I will explain this also later, okay? You will have here geophones here. These are geophones that will measure, okay, and the seismograph here. Okay, and of course you have to use a software for that. So the seismic energy is, you can use seismic energy by dropping weight. You see the hammer here is for creating seismic energy, or explosion. Okay, you can use also explosion, not only this hammer shot, but you can use also explosion. This is just to give you the seismic energy. And then P wave, it will the seismic energy will give you by dropping this the weight or explosion, will travel as a compression P wave. Okay, and is refracted by the surface material. See the refraction, this the different surfaces, this boundary is reflecting the this wave reflection. Why is it P wave actually? Because you know very well, I hope you know, we have P wave and S wave, right? the S wave is very slow. Okay, very slow. The shear wave. Okay, so we assume that the wave that is being received here, or the wave that is traveling fast, is the P wave. That's all. That's why we know that. That's how we know that it is P wave. Okay, so I will put this here, this equipment here. So when the wave front intersects a like a high velocity interface, it creates a head wave. The head wave is like here is explanation. Okay, the source here, you can see here is the source of energy is explosion, not using hammer, hitting hammer, using the hammer. It's just explosion, and the wave started here, traveling here. Okay, then at this interface, you can see here this material and this material. We have the interface here. When the wave reaches this interface, it creates like the head wave. Okay, what we are calling head wave. This head wave is almost parallel to the interface, the boundary between the two soil material. Okay, and then it return to the surface. See, like this, and this geophone will record it. Okay, this geophone will record it and send to the recording seismograph. This is how it works. Okay, the head wave. So it will go through the low velocity of a burden, like this soil. Okay, hey, don't worry, we will come back on these two later. Okay, now I just want you to understand this, how it works. So these geophones are here. This one, these are the geophones. Okay, this is why you are putting at several distances. Okay, the geophones detect this ground motion. The ground motion will be detected by these geophones. Okay, and they will send the signals to the recording seismograph. Okay, so by determining the arrival time of this refracted wave, remember, these are the refracted wave, these one are the refracted wave. Okay, so the arrival time of these refracted waves will be recorded. Okay, arrival time, determining the arrival time of these refracted waves, the velocity of the material and the depth to various interfaces can be calculated, and I will show you soon enough how to calculate the depths. Okay, the depth of this soil layer, and also the velocity and everything. Okay, so this test help to determine the stratigraphy, such as depth of bedrock. For example, you want to know at what depth the bedrock is. Okay, this is how we know, before even digging, how we know where is the bedrock. If you remember in the previous videos, we have talked like about if there is a bedrock near the surface or the bedrock cannot be reached. Okay, how will you know that there is bedrock or there is no bedrock? This kind of test can help to understand, to know the at which depth the bedrock is located. Okay, so it will help us to get that, and also it help us to get the thicknesses of the soil layers. Okay, it can estimate the depth of, for example, borrow material. If you want to make an embankment, for example, you want to make embankment and you need borrow material, you go somewhere in, and you see a very good borrow material, the surface, and you want to know how deep is this material. Is it, do you have really a lot of borrow material, or it's just at the surface, just 1 meter or even less? Okay, you can use this to know, this place, we can use this place to satisfy our project. We can get all borrow material from here, dig it, and bring it on the construction site. If you are building road, for example, okay, for the road embankment. It can also help to map faults, okay, the faults, and also fractures rock zone if the rock has some like cracks. Okay, it will help also to locate water table. Okay, how do you know if the water table is deep or shallow? And also estimate material elastic property like shear modulus or Poisson ratio. How can it do that? For example, we can, this is the wave, okay? As you can see, in this wave, you can have, there are a lot of information. By getting the wave, the V, the wave velocity, I'm saying wave, that the velocity, okay? The wave velocity. In the wave velocity, there is, as you saw, as you can see here, modulus of elasticity of the material, of the medium, okay? Unit weight, okay? And the Poisson's ratio is here, okay? So this can help us to get the shear modulus and the Poisson ratio. So the depth of exploration depend on the energy source and geophone spacing. It means the source, the energy source here, if you are using just the hammer, maybe it will not be that deep, okay? Or if you are using explosion, maybe it will not be different. It will not be same. And also the spacing, okay? The spacing of geophone you are using here, the spacing. What is the spacing between this one and this one? Okay. Yeah. So this will affect the result, the depths you are going. So it is actually possible to roughly identify soil type. Okay. Do you remember the GPR was not able to give us the type of soil? But this one, seismic refraction, can give us the type of soil we have in the underground. Okay. Here is an example of this. You can see here a cross section built from data, P wave data, P wave refraction data. Okay. You can see here soft, okay, intermediate, hard, hard to intermediate, and here is the hard one. Maybe this one is the rock, the bedrock. And you can see here the velocity measured here. Okay. As you can see, the blue one has high velocity. The velocity, the wave velocity of this one, maybe it is rock. But we will see that different material also have different wave velocity. We will see a table that can allow us to judge, maybe this is rock, this is not rock, something like that. And here are depths, okay? You can see here, the maximum here is 13 meters, okay? So as I was saying, we have here, for example, soil. These are soil, rocks. So each type of soil has like range of P wave velocity, okay? For example, sand, dry silt, and fine-grained topsoil, okay, can have this range between 200 to 1000, okay, velocity meter per second. Compacted clay, clay gravel, and dense clay sand, okay, we have this, okay. Rock also. So we have these data that can help us to know, for example, we have here 2500 and 26, for example. Okay, so you can say, this is rock. Okay, something like. So just indication. Okay, so let's come back on this figure. We will try to comment these two now. Okay, here the S, you can see S here is just the source, the energy source. Okay, one here, one is direct wave, because some wave will travel horizontally, the ground surface here, or it will be just like this one, head wave. I have explained this one, the wave that are parallel to the interface. This is what we are calling head wave. Okay, so number two here is the wave that are refracted once, only one time. So it means you have here just one interface. It means number three here is wave that is refracted twice. Okay, twice. This is number three. So it means the second boundary, the second interface. Okay, so please keep in mind the meaning of this 1, 2, and 3. And S is just the source of the energy source. Okay, so based on this, and also see here, the first soil layer, layer 1, we have here, it will give us V1, velocity, the wave velocity. V2 for the velocity of the soil layer 2, and V3 for the soil layer number 3. Okay, then we can use this kind of equation to, like, seismic refraction determine the thickness of top two layers. We can determine the H1 and H2. I will show you step by step how we can calculate H1 and H2. Okay. So these geophones, this one, they will receive three types. For example, if you take this one, okay, it will receive direct wave. As you can see, direct wave is number one. Okay, please remember that. It will receive also two refracted wave. This number two, it will receive this one. And also it will receive the one reflected, two reflected, refracted, sorry, waves. This one time refracted and two times refracted. Okay, so it means this G phone, for example, GI, replace I by whatever you want, 1, 2, 3. Okay, supposing that this one is 1, 1, 2, 3, 4. Okay, geophone, this G means geophone. Okay, so this geophone, for example, we receive three waves, the direct one and two refracted one. Okay, but of course it will be a different time. Okay, the time, this one will be fast, I mean. Okay, this one will be received first, and the second one will be received, and the third one will be received. It will depend on the depths. As you can immediately guess, the depths of this soil layer will affect the arrival time of this wave. Same here, the arrival time of this wave. As for this one, this distance will, like, affect it. So we can then plot this kind of curve. See, T1 is maybe for the, when we receive, we can get these two segments. This is distance, the distance from the source, distance from S in the horizontal axis. S is the source, right? GI. is the distance between S and GI. Okay, so this distance, you put this distance here. Distance from S to G and X. So you can get this kind of curve. Okay, for each time, what at what time, different time. Okay, what time, okay, this the first wave is received. You can plot this. What time the second wave is received. We're plotting this kind of thing. Don't worry, if you have many of the recording, you will have this kind of curve. Okay, I will show you an example how we can do that. So the next step is to determine the slope of these three curves, three segments of the curve. Okay, the thing is, the slope is just the inverse of the velocity. Okay, because this slope is time divided by distance. Time divided by distance is just the inverse of speed or velocity, because velocity is distance divided by time, right? So here we have time, okay? The slope, time divided by distance. So it is just inverse of the velocity. So this first slope is the velocity, the inverse of velocity of this first soil layer. And the second one is the inverse of the velocity of the second soil layer. And also this one, V3, see? So if you have these slopes, then you have also the velocity. And if you have the velocity, you have the slope, okay? Because remember that the recording here is just the time, arrival time will be recorded by this seismograph. It will be recorded, this time here, okay? And the distances, you know already the distance, the spacing, you know, right? You know the distances. So by knowing that, knowing the time, you know the distances, you can get the velocity, okay? Because the slope is just the inverse of velocity. Anyway, if you get that the slopes, then you can combine the information arrival time, okay? Information from this figure and the arrival time of the first signal can be used to plot this one. So you can use these two formula to estimate, calculate the thickness of this soil layer, top soil layer and the bottom soil layer. Okay. We cannot measure this third one, the thickness of the third one. I I think this is not difficult to do. Because we have V1, V2. V1 is this velocity, this velocity. Okay. The time T1, T2. Okay. You can see here this time. So it's clear now how we can obtain the thickness of the soil layers, right? So this thickness information must be verified with corresponding measurement from borehole at the site. Okay, the borehole you calculated these distances, the thicknesses of the soil layer, but you can compare the value here with the value obtained with your borehole from the borehole on the site, on the construction site. Okay. So to determine the velocity V and P, I will give you the steps. What are the different steps to determine this. First one is to obtain the time of the first arrival, okay, at various distances. The first arrival, okay, we want the first one. The geophones are located at different locations, right? So the first arrival for each geophone, you write down that time. If you go on site, after obtaining that, okay, the distance is the distance from the point of impact, the place where you are hitting the hammer or you are doing the explosion, the distance from that, okay? So next step is to plot the graph, time against the distance, okay? And graph will look like this, time here and distance here. Distance is easy to determine, and the time, arrival time, is recorded by the seismograph, okay, the device. If you plot this, then step number 3, determine the slope of these, the 3 slopes, okay? And if you determine the slope, remember that these slopes are just the inverse of the velocity, or the inverse of velocity or the slope, okay? So after doing that, then you can get the velocity, right? V1, V2. So you can then calculate the thickness of the first layer by using this formula. You have the time, T1, you have V1 and V2. There is another formula also for this, okay? But they are same. You can also calculate then the thickness of the second layer using this formula. So this is how it works. So here is example for you, okay? We are giving here the distance of geophone from the source of energy, source of disturbance, okay? Here is the distance, and here is time, okay? So please plot the graph. I am not doing this for you, okay? Please try to do it by yourself. Please plot the graph, okay? And determine the slopes. From the slope, you can get the velocity. After this velocity, use the two formula to obtain the thicknesses of the two first soil layer. Okay, so this is here. Determine the P wave velocity and the thickness of material and content. Please do it and let me know if you have any trouble getting result. Thank you. So let's go to another type of seismic survey, okay, resistivity test. This one is called cross-hole seismic survey, okay. The velocity of shear wave, this time we are talking about shear wave, this means S wave, in the soil layer can be effectively determined using the cross-hole seismic survey, okay, as shown this figure. So this technique involves drilling 2 holes. We have one here and another one here. You can see the distance here between the 2 holes is L, okay? And we can then impulse like the impulse is created, okay? After creating the impulse, at the bottom of the hole, okay, one of them, then we can receive it, the shear wave, the S wave is recorded the other in the other hole, okay? You can see here vertical velocity transducers can be recorded here, okay? Then the shear wave can be calculated using this formula, Vs, the velocity S, Okay, L divided by T. Okay, the velocity of the wave. You can do this, just distance divided by time, right? T is just the time of the wave travel. So let me put the formula here. So the shear modulus of the soil now, let's go for the ground information, soil information. You can calculate it from this formula. Since the velocity is the shear modulus divided by this is unit weight, and this is just acceleration of the gravity. Okay, you can then calculate the shear wave, the shear modulus. Okay, not Young modulus, but from this also you can obtain Young modulus, right? Shear modulus from this. Okay, so I think that will be all for this geophysical, okay, geophysical testing method. Okay, so remember, we are going for all the different type of testing. Okay, that means next video, we will talk about physical sampling and penetration test. The physical sampling we did already. So next time we will talk about standard penetration test. Okay, thank you very much. That will be all for this video, and see you soon. Thank you for your time.